Hello everybody, welcome to our lesson. Today's topic is magnets and magnetic field. This is the goal of the lesson. At the end of the lesson, you will be able to describe magnet, explain the usage of magnets, explain repulsion and attraction forces of magnets, and describe the magnetic field. Magnetism plays an important role in our daily lives. In industry, powerful electromagnets are used for lifting and transporting steel plates, scrap iron and other metals. Magnets are also used in various instruments, such as transformers, motors, loudspeakers, typewriters, video recorders, and computer memories. So, what does the word magnet mean? Why magnet? It's named after a city, Magnesia. It's a city where magnet was first found, and it's located somewhere in Turkey. The phenomenon of magnetism has been recognized for thousands of years. Ancient people first discovered the property of magnetism in lodestone. So this is basically the first magnet found. A lodestone is a naturally magnetized piece of the mineral magnetite. The lightly magnetic property of this rock specimen is demonstrated here. This stone contains iron ore, the Earth's only natural magnet. And magnets can also be artificially produced from iron, cobalt, and nickel. It means that magnets can be found in two ways, as natural and artificial. So let's define the word magnet. Magnet is an object which attracts anything containing iron, cobalt, nickel, and some alloys of iron oxide. So these materials are called magnetic materials because they are attracted by a magnet. And also we have non-magnetic materials which are not attracted by a magnet. Much like the Earth, magnets have a pole at each end, a north pole and a south pole. You may not be able to tell the difference between the magnetic poles. They behave quite differently. Magnetic pole, it's a region at each end of a magnet where the external magnetic field is strongest. So how can we be sure that magnets are divided by two, north and south? It's easy. Pay attention to this demonstration. If you put the pole of one magnet near the pole of another magnet, one of two things will happen. If the poles are opposite, they will attract and click together. If the poles are the same, they will push away from one another. So, unlike poles of different magnets attract each other, like poles repel each other. The magnetic force between a pole of one long bar magnet and that of another was described by an inverse square law as early as 1750. This law states, if, for example, the separation between the two poles is doubled, the magnetic force diminishes to 1/4 its former value, so it's decreased by 4. And breaking a magnet in two does not isolate its north pole from its south pole. Each half is found to have its own north and south poles. Magnetic forces, in fact, cannot be traced to unit magnetic poles of submicroscopic size. Indeed, magnetic forces themselves also fundamentally arise between electric charges when they are in motion. So it means you cannot find a magnet with one pole. It's not impossible. Magnet will come always in two poles. Pay attention to this demonstration. We have a bar magnet and we feel iron oxide, iron alloys above that magnet. What's going to happen? Look at here. Iron fillings are ordered around the magnet. Of course, they feel a magnetic force. So magnetic force, you see, acts differently at each region of a magnet. This means that around the magnet we have something that's invisible. And we call this magnetic field. Magnetic fields are areas where an object exhibits a magnetic influence. The fields affect neighboring objects along things, called magnetic field lines. Now, let's go to the FAT simulations. We before mentioned that magnet must have a field around. How can we be sure? To test that, we need a compass. So, compass will show the reaction with the magnet. Pay attention for the arrow of a compass. You see? Compass changes its direction every time I change its position. But how can we picture a magnetic field? There are many ways of illustrating magnetic fields. Normally, magnetic fields cannot be seen with a naked eye. But we can put a tiny magnets around the tiny compasses around the magnet and see how they are affected. You see, everywhere at every region we have different directions for the compass. And look at here. When I change a magnet, the compasses are changed. This bright side of a compass means that we have some strong force compared to this region. There we have a weak force. And what if I decrease strength? You see? So this is one way of showing magnetic field. And you should note that Earth itself is also a magnet. Around Earth we also have a magnetic field, and one of the uses of this field, it protects us from little rays, ultraviolet for example. Let's make the conclusion. We said that magnetic field cannot be traced with a naked eye, but we can explain and we can illustrate magnetic fields using compasses. I've drawn here a magnetic field lines. This is another method of indicating a magnetic field, and it's suggested by a Maxwell. He said that it will be effective if we describe magnetic field with the lines. So pay attention to the direction of the compass and direction of the magnetic field lines. Yes, they are same. Actually, magnetic field lines must be tangent at that point. Also, you should note that magnetic field lines started from the North Pole and ended at the South Pole. So let's do another demonstration. Now we have not one bar magnet, we have two bar magnets, and as in previous, we will feel iron fillings. The result of the experiment is shown here. we see two different pictures. Actually, I've just flipped the pole of one magnet. It means we have two types of interactions here: repulsion and an attraction. I think you can guess from the picture where we have repulsive force and where we have an attraction force. See, the magnetic field lines are joined here. It means these two magnets feel a force of attraction. Here, magnetic field lines are not joined. We have some space here with no magnetic field lines. And these magnets feel a force of repulsion. Let's illustrate it by lines. Look at here. This is a force of repulsion, and pay attention to the magnetic fields, and this is force of attraction. Now we should learn the properties of magnetic field lines. We have some main properties. First is magnetic field lines always start from the North Pole and end at the South Pole. And second property, maybe you've noted, magnetic field lines never cross each other. And the density of the field lines is directly proportional to the strength of the magnet. It means simply, if magnet is weak, you have less lines. If magnet gets stronger, you will have more lines, denser lines. This is the main properties of a magnetic field lines. And the magnetic field lines can be an origin of an art. Look at here, how beautiful. Now, magnetic field, it is represented by a letter B in equations, in formulas, and it is measured in standard unit as Tesla. Simply, magnetic fields is measured in Tesla. Now, our lesson comes to an end, and at the end of the lesson I will ask you a question. At which points in the figure are the magnetic field vectors in the same direction? Feel free to leave a comment below and check your understandings. Thank you, and don't forget to subscribe and share our video.